Okay, guys, we are in chapter magnetic effects of electric current. So, chapter magnetic effects of electric current. So, by using electric current, what type of magnetic effects we are going to get? So, mainly this chapter is depending on electricity and magnetism. So by using electricity, how can you create magnetic field or magnetic effects is the main central idea. While coming to basics, in last lecture we have discussed about magnets, right? Magnets, for magnets there will be poles, two poles, north pole and south pole. There will be no east, there will be no west. There are different concepts. Simply to say, if you take one bar magnet and if you tie that bar magnet by using a thread, and if you hang it in free space, if you hang it in free space, automatically, for example, this is north side of the bar magnet, this is south side of the bar magnet, south pole. After a few time, after some time, that magnet will come and rest in one particular position and it will not move further. There will be no torque in the sense turning effect. Turning effect will not be there, no torque, and it will be static. Pole of the bar magnet, which is showing the direction, is geographic north of Earth, and south pole of the bar magnet is facing towards geographic south. So north pole of the bar magnet is showing Earth's north direction. South pole of the bar magnet is showing Earth's south pole or south direction. So it will not turn towards east and west, so that there will be no east and west poles for the bar magnet. Always bar magnet will be turning towards north and south direction only, and magnetic poles, magnetic effects will be there at north pole and south pole. There will be no magnetic effect towards east and west, so there will be no east and west for the bar magnet. Very simple description. Okay, there will be two poles, north pole, south pole, and we have seen attraction, repulsion. While coming to like poles always it will repel. Example, north and north will repel, south and south will repel. Next, unlike poles, always there will be attraction. There will be attraction. Example, north pole and south pole will attract, south pole and north pole will attract. And we have seen different types of magnets. So this is bar magnet, you can see, where there will be one north pole and one south pole. Ring magnet. This is horseshoe magnet or U-shaped magnet, we can call U-shaped. This is disc magnet, which will be flat. This is magnetic needle, where we will use in magnetic compass. Magnetic compass, which is used to show some directions. Sailors and in aeroplane navigations, you can find this magnetic compass. And while coming to poles, I told you there will be north here, south here for a bar magnet. For horseshoe, north one side, south one side, either. If it is south here, north will be here, like that. So compass also, if it is north, it will be south. You see, maximum bar magnets or magnets which you are using in your laboratories, it will be red in color. There is no specific thing why it will be red in color, just for identification, that's it. And if total bar magnet is red in color, they will not represent n south, etc. what they will do means, with a white color paint, they will give one small dot. That's it. That dot represents North Pole. Like that, you need to identify poles. So from this concept, what we have learned, different shapes will be there for different magnets and different uses. Then while coming to this, around every magnet, so if there is a magnet, so around this magnet, definitely there will be field. That field is known as magnetic field. We can compare this magnetic field with gravitational field, but in gravitational field there will be only attraction. You see, gravitational field, there will be only attraction, isn't it? There will be no repulsion. Can you see any object which will be repelling from the earth's surface? Don't confuse between repelling and bouncing. Sir, if I take a rubber ball, if I throw on ground, it will touch the ground and it will repel. No, it will not repel, it will bounce. Don't get confused. So there will be only attraction. If you throw any object, it will fall down because of the earth's attraction. But while coming to magnetic field, you can find attraction and also repulsion. That is a difference here we can find. And magnetic field, of course, you see gravitational field, it is invisible, we cannot see it. Magnetic field, of course, that is also invisible, we cannot see it. But inside magnetic field, if you arrange few iron fillings, or if you keep few iron fillings, automatically iron fillings will be arranged in one particular order. I'll show the diagram here. Can you see here? So these are real pictures of iron fillings which are placed around magnet. You can find, you can take one chart and you can place magnet under the paper or under the chart, place chart or paper on the magnet and drop few iron fillings. You can find all iron fillings are arranged like this. You can see all iron fillings are arranged, and if you draw lines, it will become magnetic field lines. That's it. Of course, with our naked eye, we cannot see the field, but by using iron fillings, we can see the field. So iron fillings are helping for us to see the field. You can see this, you can consider this one as North Pole, this one as North Pole, and this one as South Pole, and all iron fillings are arranged like this. You can find that, right? So by that, what we can conclude, if there is a magnet, around magnet, if there is magnet, around magnet there will be magnetic field, and magnetic field, inside that magnetic field there will be magnetic field lines. So 3 words you have to remember: magnet is different, magnetic field is different, magnetic field lines are different. So from this, what we can conclude, guys? These are the lines of magnetic field. Here we have discussed in last lecture 2 points. What is the first point? Magnetic field lines are closed. Simply to say, it is closed loop. You can find from North Pole, one magnetic line is traveling and it is traveling towards south. Again, what will happen, you know, that will travel towards north like this. Inside it will be like this. This is the direction. That is the first point we can remember. And second point, while coming to direction of field lines. Number 1, it will flow from north pole to south pole outside. Second direction, south pole to north pole inside. You see here, outside means outside of the magnet. You can find magnetic field line. You can see the direction here, which is flowing from north to south. Here also north to south direction outside. Here also you can find ray, it is going from north. From north it is moving out, right? But inside you see, it will be south. This is the direction you can observe, south, and south to north again. From north it will be moving out. So directions are so important. If you are drawing down, again from north it will go out. And most important third point, magnetic field lines never intersect. It will never intersect means, consider if there is a line like this, magnetic field line, if it is going like this, there will be no another magnetic field line will cut this. No, there will be no intersection. There will be no intersection. There will be no cutting of the lines. Why? Because this magnetic field line will represent direction. Direction, or it will represent pole. At the single point, there is no chance of having two poles. At single point, there will be no two poles. It is not possible, isn't it? If you take magnet, here there will be north pole, this side there will be south pole, here only north pole, here only south pole. Is that possible? No, it is not possible. So two poles at the same point is not possible. So magnetic field lines never intersects. So while you are drawing this, one line should not touch another line. This also we'll discuss in our fourth lecture. Third or fourth lecture we'll discuss why two magnetic field lines will not intersect, and how to calculate, how to see the direction. If it is going, means there will be north pole, right? If there is any another line like this, means here also there should be north pole. So here north pole and here north pole. Is that possible to have? No, it is not possible to have. If you keep two magnets, you may get doubt. If I keep two magnets, what happens to the magnetic field? That we'll discuss in next lecture. So we have seen one experiment yesterday, I mean in last lecture, this one. If you take bar magnet and if you place magnetic compass, you can see here this red color is representing north pole of the bar magnet, and this blue color side is representing south pole of the bar magnet. Now if you see magnetic compass needle, for easy identification we can go red color as north and in compass white color as south. Now we can see this red color is facing towards the south. Simply to say north and south, here also north south, and it will attract. But while coming to here, it will be repelling. So you can see the direction here in this diagram particularly we can see one thing, head and tail, compass needle we have. This is head and this is tail. Head always represents north pole, tail always represents south pole. Here you can find this is north pole of the bar magnet, and here we have south pole. And here compass needle you can find which is showing this direction. This is north, this is south, and south will be attracted, and it is showing this direction. Here we have this, here we have this, and it is coming like this. So what we can do, we can draw a magnetic field line like this, isn't it? Here also down we can draw magnetic field line like this. Okay, 2-3 lines we can draw. And directions are important. From north it is moving towards south. From north it is moving towards south. Inside, south to north. So these are the basics we have learned in last lecture. So this also same experiment. This is magnet with north pole and south pole. Then magnetic compass needles are placed to see the directions. Here you can see each of these showing different directions. Right here, this you can find which is showing this direction, here which is showing this direction. So like that we can draw. So from this, yeah, same thing we can say. Whenever you take magnet, around magnet there will be magnetic field, and magnetic field will be arranged by means of magnetic field lines. And here this diagram is showing about directions. Already we have learned those directions. There will be 2 directions, outside and inside. While coming to outside, magnetic field lines will be moving from north to south. Inside, south to north. You must remember, this is so important. There are chances of asking questions in your board examination also. So you are familiar with the diagram. You must draw diagram if they ask in your examination. How to draw this diagram? Simple. Draw one rectangle, represent north pole and south pole. From north, draw one curved line to south. You can draw second curved line, you can draw third curved line. Make sure to represent its direction north to south. And from bottom also, downside, you can draw one curved line, second, third. Here also same, north to south. Directions are so important. And while curves are expanding, it will become straight line. Simple. Take a circle, cut that circle, and if you extend that one, it will become straight line, isn't it? That's what is happening here. Here curves angle will be less, here curves angle will be great, and here if you see, actually this is the extension. This is extension. Here also, this one is also an extension. So like that, if you take a circle and if you cut that circle here and if you extend this, it will become definitely a straight line. That's what is happening in the middle, you can observe. So if you hold this point and this point, if you arrange it, automatically it will become curves like that. So you need to draw complete diagram. So from north, what you can do, one line like this, one line like this. So these are extension lines. Means it is incomplete lines. We didn't complete this. Okay, if you want to complete, diagram will become very big. So like that, you have to draw one straight line in the middle, and arrow marks are so important. So from north it is moving, from north it is moving, from north, from north, from north, and it is coming to south, coming to south. All these rays are coming to south. Like this, you need to draw diagram that should be neat. So in today's lecture, we need to discuss about magnetic field due to current carrying conductor. We will discuss now. So we are in topic magnetic field due to current carrying conductor. You see the name, guys. You see the name magnetic field due to current carrying conductor means first we need conductor. Second, to that conductor we need to pass some current such that that conductor will become current carrying conductor. Means electricity is present inside that conductor. That is the meaning for that. Current carrying conductor means conductor which is carrying some current, means there is presence of electricity. Okay, consider there is a conductor on straight line wire where there is current. Current is represented with the letter I, isn't it? I. If there is current, then what? What means definitely there will be magnetic field. Magnetic field around that conductor. How come? How come magnetic field around that conductor? We will see. Hans Christian Ørsted was a scientist, one of the leading scientists of 19th century. He played a crucial role in understanding one of the branches in physics, that is electromagnetism. In electromagnetism, we have two parts, electricity and magnetism. How he discovered? In 1820, guys, no need to remember these years, centuries, nothing. This is just for your information. In 1820, he accidentally discovered that a compass needle got deflected. Compass needle got deflected when an electric current passed through a metallic wire placed nearby. So first let us try to understand this circuit, then easily you can understand that line. You see there is a circuit with some key, there is a resistor, of course not needed. There is cell or series of cell, that is battery, and because of that battery there is current inside this circuit, and it is open circuit. This is point X and this is point Y, where just arrange one conductor. If you arrange conductor and if you switch on, what will happen? Definitely current will pass. Current will pass through this limb, it will pass through this side, and automatically current will pass through conductor. Now this conductor is becoming current carrying conductor. Now place one compass needle. You see, first let us place first compass needle here, second compass needle here. Now in first case, don't switch on. I mean there is no electricity, let us assume. If there is no electricity, that compass needle will be showing this direction. When there is no electricity or no current, it will be showing this direction. As soon as switching on, what will happen? Current will be present in the circuit and current will pass through the conductor, and automatically you can see this compass will deflect. It will deflect. Second case. In first case, there is no deflection because no current. In second case, it got deflected. Why? Because there is a current. Here you can see this activity 13.1, which is present in your textbook. Take a straight thick copper wire and place it between X point and Y point. Electric circuit as shown in figure. Place a small compass near to its copper wire. Place here. See the position of the needle first. Pass the current through the circuit by inserting the key. Observe the change in the position. You see, observe the change in the position of compass needle. Why there is change? Because whenever current is passed through the conductor, magnetic field will be present around the conductor. This is important point. You must note down in your running notes. So, well, coming to this activity 13.4, same thing guys. First what we have to do here, take long copper wire, 2-3 cells of 1.5 volt each and a plug key. Connect all of them in series as shown in figure 13.5a. Okay, fine. Here you see there are two diagrams. This is first diagram, or you can say first circuit. This is second circuit. You see in first circuit there is key. Second circuit also there is key. First circuit there is a battery. Second circuit also there is a battery. But what is the difference means? In first circuit, positive is towards left hand side, negative is towards your right hand side. And while coming to second circuit, negative is towards left hand side, positive is towards your right hand side. That is the only difference. Now what you can do, you can consider this is one point and this is another point. First of all, it is an open circuit. Here also it might be open circuit. Take one copper wire, connect between 2 points and it will become closed circuit in two cases. If you connect copper wire, it will become closed circuit in two cases. Now place one compass needle on the copper wire. Consider we have placed one compass needle like this. And you see here there is a direction, right? It is north, it is south. So always compass needle will show north and south direction only. In second condition also we have placed one compass needle. It will be showing north and south only. When there is no power, when there is no current in the circuit. Fine. So before switching on, before inserting the key, if there is no here, if there is no current in circuit, there will be no deflection in compass. Most important. If there is no current in circuit, definitely there will be no deflection in compass, and it will show north south direction only. North south direction only. Next, what we have to do? You need to switch on or you need to insert a key in both cases. If you insert a key in the both cases, what will happen? You see, this is positive, right? Left hand side. We know direction of current. It always from positive to negative. You can see the direction positive to negative. Like this it will move. Now, while coming to second case, direction should be this direction, right? From right hand side it should move. From positive, it will move top and it will go this direction. It will come in this direction and it will move in this direction and it will reach to negative. You see, in first case, current is clockwise direction. Current is clockwise. Current direction is clockwise. Here I will write. In first case, current. In second case, current. In first case, current is clockwise direction. In second case, current is anti-clock. vice direction, anti-clockwise, isn't it? Now you see, first of all, before switching it on, that compass will show north and south. Of course, here also it will show north and south, but after switching on, because of flowing of current downwards in the conductor, you can see the deflection here. Current is moving downwards, deflection is towards, it got deflected like this, right? Towards east. Now here, second case, current is moving upwards. If it is flowing upwards, so instead of this direction, there is a turning effect like this. Here you can find like this, and it is showing this direction. So that is a concept you need to understand here. So in first case, because of clockwise, there is a turning towards east. In second case, because of current direction changed anti-clockwise, that turned towards west. So what concepts we have learned here by these experiments means, if there is no current, there will be no deflection. That's what we have learned from these experiments. First point. Second point, if there is current in a circuit, definitely there will be deflection. That we have learned. And third point, what we have learned, if there is change in direction, if there is change in direction of current, if there is change in direction of current, there will be change in direction of deflection. There will be change in direction of deflection. Most important point, these are also you need to write, you need to remember, because all concepts will be revolving around these. And so these are the concepts we have learned. Last topic, magnetic field due to current or around current carrying conductor. Magnetic field due to current carrying conductor, and the conductor should be in straight line. That is the case. There are three cases. First case, that should be straight. Second case, single loop. Third condition, multiple loops. That we'll discuss in next lecture. First we'll see straight. Guys, you see there is a very simple circuit diagram where circuit is connected to ammeter, rheostat, variable resistor or key, and main important thing is battery. Okay, and consider there is a conductor. You take one paper, poke conductor through the paper. There should be a paper and one conductor you have to pass through the paper. Okay, now don't switch on. Before that, what you have to do, take few iron fillings and try to sprinkle few iron fillings on the paper. And if you see, iron fillings will be at rest. There will be no deflection. There will be no motion, nothing if there is no current. Now switch on. If you switch on, what happens? Eventually inside this conductor, current will pass. If current is passing through the conductor, what will happen? Magnetic field will be produced. You see, flow chart you have to remember. Conductor. To the conductor, if you are passing current, what will happen? Definitely magnetic field is produced. Magnetic field is produced. Where? Around conductor. Around conductor, magnetic field is produced. Now, what is the shape of field? What is the shape of magnetic field? We know while coming to bar magnet, magnetic field will be like this, like this, like flower or something you can say, right? Like mushroom, like flower, it will be like butterfly, whatever shape you want, you can say it, mushroom, butterfly, something. But while coming to straight conductor, what is the shape means? Circular shape, remember? Circular shape. So shape of the field is circular. Here you can find after passing current, all these iron fillings will be arranged. In circular path. You can see all iron fillings are like this. Automatically it will arrange. Here you can see all iron fillings are arranged in circular path. This point you have to remember. You see this one, right? If this is a current carrying conductor, this arrow mark is representing current. These arrow marks are representing magnetic field. So it will be in circular path and it will be continuously moving. Continuously magnetic field will be in motion. If current is in, what is meant by current, guys? Current is nothing but flow of electrons. Flow means nothing but motion only, right? If there is motion in electron, there will be motion in magnetic field. And if there is no motion, then definitely there will be no current. If there is no current, there will be no magnetic field. Simple. There is no magnetic field. Now, this can be expressed using right hand thumb rule, very easy to express. Consider this is current carrying conductor, imaginary conductor. If you hold that conductor, of course, we won't hold it because if current is flowing, we may get shock, isn't it? So just assumption. It is just assumption. If you hold a current carrying conductor by using your right hand and opening your thumb and closing all your fingers, here you can see this diagram. Only thumb should be open, remaining all 4 fingers should be closed. And if you hold a conductor, this thumb will represent direction of current. This thumb will represent direction of current, and all remaining 4 fingers will represent direction of magnetic field. Simple. Now consider there is a current carrying conductor. If you are holding this thumb is representing this direction, right? So up, twinkle fingers like this, right? So around this conductor there will be magnetic field. Now this is current carrying conductor, thumb is in this direction, thumb is representing direction of current. So this is I, wrinkle fingers are like this, fingers are closed. So around this conductor there will be magnetic field. Here also you can find another diagram. This is wire, this is thumb is representing direction of current, wrinkled fingers representing magnetic field. So if current is moving down, same thing. If current carrying conductor is down, this thumb is representing direction of current, wrinkled fingers. You see, fingers are closed like this, like this. So direction also will be like this. Like that you can draw a diagram. So you see wrinkled fingers are closed like this. So magnetic field will be like this. Simple. So that is right hand thumb rule. That's it in this lecture. In our next lecture, we'll discuss this topic. Magnetic field around straight carrying conductor. Magnetic field around single loop. Single loop means you need to make it circle that wire. And third one, multiple loops. How magnetic field will be present. So that's it in this lecture.